Hello and welcome. So we were discussing about the application of symmetry rules in case of electronic spectroscopy. So similar to our approach in case of vibrational spectroscopy, we started looking at the wave functions of the for the electronic transitions, and the corresponding transition moment integral that we are looking at. So the transition moment integral involving all the different components, for example, vibrational and electronic as well as spin. So rather I should say is the orbital and the spin. So ultimately what we got by transition moment integral as the product of three integrals. So the first one we got as multiplied by the and so these were the three integrals that we got ultimately for an electronic overall electronic transition, and we came to this by using the condition of orthogonality of two electronic levels. So we also mentioned that this particular integral is so-called Frank-Condon factor. So the Frank-Condon factor gives me the overlap between the wave functions of the vibrational levels at the lowest electronic state and that in the upper electronic state. Okay, so what it gives me? It gives me the overall modulation in the electronic spectra. Correct? So the second part, this forms the basis for orbital selection rules. And the third one, it forms the basis for spin selection rule. Okay, so let's start with the spin selection rule part. Okay, so this is probably the the first thing that one should look at, whether this this particular integral is vanishing or non-vanishing. So before going even into the detailed discussion about these individual three integrals, so since this is my overall transition moment integral, the allowedness of an electronic transition will be affirmative if the overall integral is non-vanishing. Otherwise, if any one of this integral is 0, then the corresponding transition will be forbidden. Now, when we talk about this particular part, so what we look at? So this is a transition between two states having two spin states. Right? So if suppose I have a ground state, suppose this and if I want to make a transition to say or maybe say 1 to say so in this kind of transition, if I have to look about look for the allowedness of this particular transition, that is whether it is spin allowed or not, then only thing I have to look for the spin multiplicities of these two states between which the transition is taking place, or one is thinking about having a transition between these two states. So if this two states have different spin multiplicities, they are going to be orthogonal, right? Because this spin wave functions, having two different multiplicities, they are completely orthogonal. So therefore, until and unless the spin multiplicities of the two states involved here, the transition is forbidden. So therefore, a case where spin multiplicity 1 to 1 is allowed. Okay, so that means if I have say singlet state, I can have a transition to a singlet state having spin equals to 0. So spin multiplicity is 1. Similarly, I can have say triplet to triplet is allowed, but a singlet to triplet is forbidden, or a singlet to a quartet is forbidden, while quartet to quartet or singlet to singlet is allowed. So just one has to look at the spin multiplicity, and one can easily figure out whether the transition is spin allowed or not. So next, have a look at the orbital selection rule, right? So that is our this particular integral. So if I just take out this integral, what I have two electronic states and the transition involving in between those two states. Now just like what we got in case of vibrational transitions, here also it has to be handled in the very same way. So in this particular case, one has to look at the symmetries of each of these functions. So the situation is very similar to condition when I have three different functions and I'm trying to find out the value of the integral. So here I know that this particular these two wave functions and the operator, all of them individually transform according to the one of the IRs of the point group for the molecule. So therefore the allowedness of this particular transition will depend on the direct products of those irreducible representation to which this belongs. Therefore my situation is now is such that if I have gamma of psi e prime, gamma of mu e, and gamma of psi e, this direct product, so where these individual gammas are the irreducible representation according to which these individual functions transform as. So this is a triple direct product, right? We have three different irreducible representation and having a direct product of between them, among them. So this triple direct product, if it gives the totally symmetric irreducible representation as a result, or it contains the totally symmetric IR as one of the component, then this transition will be allowed, right? So as usual, this is a dipole moment operator, so it depends on x, y and z Cartesian coordinate systems. Now for an electronic transition where the ground state is totally symmetric, suppose I have an electronic state which is totally symmetric when it is in the ground state, then simply my solution becomes such that I will look for whether this excited the IR corresponding to the excited electronic state contains at least one of the Cartesian coordinates x, y or z as its basis. Then only I will have the total integral as non-zero, right? So therefore an electronic transition for a totally symmetric ground state will be allowed only when the excited state has either x or y or z, or maybe x, y or x, y, z all as its basis. All right. So or otherwise, in general, this is the thing one has to look at the triple direct product of these functions, and you see whether the transition is allowed or not. So for example, we will take the case of benzene molecule. So if I take for benzene two states like 1A1G, and then I have a transition to 1B2U, correct? So if I try to make a transition like this, then first place the spin multiplicity is fine, so it is spin allowed, no problem about that. But whether it is orbitally allowed or not, that one has to figure out. So what I have to do, I have to see A1G, it corresponds to totally symmetric irreducible representation, correct, for the D6H point group. Therefore I have to see whether this one contains either x or y or z as its basis function or not. So therefore I will again look at my character table. So character table for D6H point group, if I look at, then I see that this B2U B2U does not transform either according to x or y or z. Okay, so I can immediately say that this transition is orbitally forbidden, right? So if I want to look at this problem even more explicitly, then what I have to do, I have to take a direct product of A1G and the irreducible representation according to which this dipole moment operator transform as, that is I have to look for the irreducible representation for which x, y and z form the basis for. So if I look at that, then I see that z forms the basis for A2U. So and x and y form the basis of E1U. So then I have to explicitly do the direct product. So I wrote it in a particular way that you will be seeing in most of the books related to this electronic spectroscopy. So here A to U forms the basis for for Z axis, while X and Y transform as U1U. Now for the operator I use the small letter, okay, so that in many cases is used. So this two terms within the parenthesis means that actually we are doing two separate direct products. So first with A1G, A2U, B2U, one direct product, and also A1G, A1, E1U and B2U. So two different direct products. So after doing that, what I get B1G and E2G. Okay. So this is for the first one, this is for the second one. So these two are not the totally symmetric IR, right? So clearly this transition is orbitally forbidden. So that one we have already seen. So in either way you can go. If you are not comfortable in doing in this short way, you can do it explicitly in this format and get the result. If the result does not contain totally symmetric irreducible representation, the transition is orbitally disallowed. All right. So we will look at this overall electronic transitions in one particular molecule in greater detail that we said maybe a week ago when we were dealing with the symmetry adapted linear combination of naphthalene molecule. There we form the states by solving the secular equations and secular determinant, and using Huckel's approximation, and then ultimately using the Hund's rule and Pauli's exclusion principle, we filled up the orbitals. Orbitals were formed by the linear combination of p pi orbital of the carbon atoms. So that we will come shortly. So at this point I'd like to mention one particular thing that many of you in your inorganic books you have or courses you have heard about the forbiddenness of certain transition, particularly in case of say metal complexes, right? And you have heard about Laporte selection rule. So what is this Laporte selection rule? In this context I will mention that. So Laporte selection rule is particularly important in case of centrosymmetric molecule. So in case of metal complexes, what you have, this ligands form, mainly the sigma bonds, and the metal orbitals they form the non-bonding electrons, non-bonding orbitals. So metal, the d electrons, you have states having T2G and EG symmetry. So in a transition from a T2G to EG, okay, which is nothing but a transition between two type of d orbitals. So these type of transitions are known as dd transition, and for centrosymmetric molecules such dd transition is forbidden. So this is what Laporte selection rule tells me. Now why is it so? If you look at the transition moment integral here, so what you will find that these d orbitals in case of centrosymmetric molecule, they are of G type, correct? So because if you do an inversion operation, so nothing happens to this d orbitals. If you look at the component functions, like either it will be xy or xz, or x square minus y square or z square, like, so all these functions are invariant to inversion. So therefore you have a dipolar transition where operator is of U type, while the transitions are taking place between two G type orbitals. So therefore the overall transition moment integral becomes U type, and therefore the value is 0. So this type of transition in metal complexes, for centrosymmetric metal complex, is disallowed or forbidden, and this is what we have as Laporte selection rule. All right, now let's move our attention to the other part, that is particularly this part related to the Frank-Condon factor. Now we have looked at the vibrational transitions and the corresponding selection rule, how to get those things. Now here, when we were discussing about the allowedness of a transition involving two electronic orbitals, there we assumed that transition was taking place from V equals to 0 of the lower electronic state to the V equals to 0 of the upper electronic state, right? So the situation was something like, so this is V prime equals to 0, and here it was V equals to 0. So we had a transition like this, so that both of the vibrational states are at their ground states, and therefore belong to the totally symmetric IR. And I didn't have to think about the symmetries of these two, because automatically it is taken care of. Now what will happen if there are vibrational states involved which are not totally symmetric, right? So what will happen if I excite from V is equal to 0 to V is equal to V prime equals to 1 here? Okay, so I should think about a transition which will have both vibrational transition as well as electronic transition. So altogether this is known as vibronic transition. Now though here you can say of course my vibrational it is situated on one vibrational state to another, I am having another vibrational state, but since both of them are the ground vibrational state, so we call this as if it is a pure electronic transition. There is no contribution coming from the vibrational states. Now if I think about a situation where I have and then this, so you remember that we have earlier decoupled this, right? And you have d tau. So this is my transition moment integral for a vibronic transition, right? So here you can see that depending, I have to consider the symmetries for both electronic state as well as the vibrational state. So if I have a situation where the symmetry of this vibrational state is different from this one, then the whole scenario changes, right? So one particular example I will give you. Say for example, we were talking about this DD transition in case of centrosymmetric molecule. Now if I have instead of, say, at ground level, the other vibrational states are Girardet type. If you look at the corresponding wave function for vibrational state. Okay, so if I find an Ungeradet state here, at that point what happens, your overall centrosymmetry of the problem is broken. Now, the transition, the pure vibrational transition, which were, the pure electronic transition, which was not allowed here because of this, vibronic coupling, I can have a transition which was earlier forbidden, now can be partially allowed. Okay, so rest of the things are exactly similar to what we did in this particular case of electronic just orbital transitions, right? So all I have to do, I have to now worry about the irreducible representation according to which each of these functions transform as, and have the direct product and try to find out whether or not the totally symmetric irreducible representation is contained in the result or not. So we will stop here today, and in the following class we'll come back with a particular example of that naphthalene molecule for which we formulated the states, their energies, and we will try to see how first place we have to find the symmetries of the states, find the symmetry of the orbitals, the states, and then can we comment on the allowedness of certain transitions or not. Thank you very much.